What I have here is a thermometer and some plasticine. I'd like to do a little demonstration regarding radiant energy, or absorption of heat via electromagnetic waves. Right now, both of these are under a light, and they are both receiving some heat via electromagnetic waves from my light bulb, as well as heat from my room. Eventually, what will happen, both of these items will come to room temperature, and an equilibrium will be achieved. Whereas it's going to absorb some electromagnetic waves, the plasticine that I have here, and it also will re-emit that same amount of energy, such that it will be at equilibrium. And the thermometer will be doing the same thing. And the thermometer itself is measuring the temperature here at the tip. Right now, they are both absorbing energy and temperature, in effect, from my lights, and they ought to be close to about the same temperature. So let's find out. Right now, the room temperature is at 21.8, and let's see what the plasticine is at. It's been absorbing energy, and it too is at 21.8. So both of these items are absorbing energy and re-emitting the same energy back into the atmosphere, such that they are at equilibrium with the room temperature. This can be explained mathematically with this equation right here. And let's look at that equation right now. This equation is known as the Stefan-Boltzmann law of radiation. And this is electromagnetic radiation that we're talking about. In other words, light energy. This equation, Q is equal to E sigma temperature to the power of 4 area times time. Let's look at these variables. Q represents radiant heat. I like to put in radiant heat energy because it has units of joules. E is known as the emissivity. It is a dimensionless number. Characterizing the surface of the object. It indicates whether an item will absorb heat quickly or reflect heat, or electromagnetic waves, shall I say. And E has a value between 0 and 1. Dimensionless number. You can find different materials will have different emissivities. Here is a chart. There we go. Emissivity values for various materials, and 1.77, 0.05, 0.9678, all the way down depending on the material. So different materials will have different emissivity values somewhere between 0 and 1. And sigma, well, this is the Stefan-Boltzmann constant. It has a value of 5.67 times 10 to the minus 8, and the units are joules per seconds, meters, Kelvin to the power of 4. This constant is in our formula sheet. Here it is here, sigma. Oh, it's meter squared, my mistake. I'll change that to seconds meter squared, Kelvin to the power of 4. This is temperature, surface temperature in Kelvin. In this particular case, we don't have a delta T, so it has to be in Kelvin. That is the go-to temperature or unit for temperature. A. And I'm going to go down here. This is the surface area. In equation 33, A represented the cross-sectional area. Then this one is the surface area. So if I had a box, and this box, there was a fire inside of this box, and it was getting hot, it will emit heat outward via electromagnetic waves in all directions from all surfaces. Therefore, this area is that surface plus that surface plus that surface, one in the back is there, all the way around. It is the surface area, and that will be in meters squared. And little t is time in seconds. Let's have another look at this, see what happens. Temperature, I moved the thermometer to another spot of the room. It's at 20 degrees, and let's see what happens to the plasticine. Theory says it should have stayed the same temperature as the thermometer. It is both absorbing and re-emitting energy, but of course right now it's absorbing heat from my light. Eventually it comes to temperature, and equilibrium will be achieved between the two of them.